We're going to go ahead and talk about the kinetics of a reaction lab. Um, this lab is long and there's a lot to it, but I like this lab a lot because I feel like it does a really good job of showing everything we've been talking about in this unit so far, um, and basically how it's determined experimentally. So how we would design an experiment to test the rate of a reaction and test what different reactants do to the rate of the reaction and that sort of thing. Okay, so the experiment that we're going to be working, experiment we're going to be working with here is an experiment with the oxidation of iodide by bromate. Okay, and that's going to be in the presence of an acidic solution. A lot of times, when we get to a little bit more about the electrochemistry, we're going to talk about how a lot of times these redox reactions happen in acidic or basic solutions to help them along. So the reaction's somewhat slow at room temperature. There's a lot of background information in this lab. And it's showing you the rate law for this thing. Now, the thing is, we don't know exactly what the rate law is because we have to figure that out experimentally. We don't know what the exponents are. Okay, so we've got our I minus concentration, our BrO3 minus concentration, our H plus concentration, and we want to figure out how changing the concentration of those things affects the rate so that we can write our rate law. So this is showing down here a little bit more, the I2 plus 2S2O32 minus, showing a little bit more about how the reaction is going to occur. There are actually two reactions happening here. Let's see what else. A good graph on activation energy, and it talks about what activation energy is in case you need to brush up on that. And then it gives you the equation for the activation energy. And it talks about catalysts, and if we have time, hopefully we're going to get to the catalyst part of this lab as well. Okay, so 4 parts to the lab, sorry. The first part, you're just going to measure the volume of a drop of solution using your pipette. Okay, that's not difficult, but that's the first thing you have to do in order to be able to do the rest of the lab. It's going to save you a lot of time rather than having to figure out volumes and stuff like that. You can measure the volumes based on drops. Part 2, we're going to determine the reaction rate and calculate the rate law. That's by changing all the different concentrations and stuff like that. Part 3, we're going to determine the activation energy, and we're going to do that by changing the temperature at which the reaction occurs. And then we'll graph this thing and figure it out from there. And then part 4, if we have time, we're going to observe the effect of the catalyst on the rate of the reaction. Okay, so those are the different things we have going on in this lab. Like I said, there's a lot to it. Hopefully we'll get to all of it. This chart right here is going to help you as far as how much you're adding to each thing for each experiment. And then we got some pre-lab questions here. Okay, and so the first pre-lab question, pretty simple because it's just showing. Let's see here. Make sure we know how to do this. The following rate data was collected by measuring the time required for the appearance of blue color due to the iodine starch complex. Okay, so we're measuring these things in molarity. Basically, the first thing you have to do is figure out the reaction rate. Now, it's pretty clear on how you do this. You divide the change in molarity divided by the time that it takes to do this. Okay, so you'll end up with molarity per second. So for the first one, it says calculate the reaction rate for each trial by dividing the concentration of the iodine formed by the reaction time. So we're doing this with respect to the iodine as far as the rate. When you measure the rate, you pick one of the reactants, usually, sometimes one of the products, but usually one of the reactants to figure this out. Okay, and so the way we're going to do this here, basically you're just taking the rate for trial 1 here. Let's see. Okay. Um, look at this here. Okay, in each child, it says the blue color appeared after 0.0020 molar iodine had been produced. Okay, so we're measuring this with respect to iodine. I apologize. Let me erase this here. Okay, so we're measuring this with respect to I2. Okay. Got that wrong. So we are measuring it with respect to one of the products in this particular instance. And it's saying that after 0.0020 molar iodine had been produced, then the blue color appeared. Okay, so we're measuring how long does it take for the blue color to appear. So in each of these cases, just like for the first one here, we're just taking 0.0020 molar divided by 270 seconds. And that's going to give us our rate in molarity per second. Okay, and then for the second one, we'll do the same thing, 0.0020 molar divided by 138 seconds, and then for the third one, divided by 142 seconds. That'll give you the three rates there. Okay, and then we're going to compare trials 1 and 2 to determine the order of the reaction with respect to iodide. So after we figure out what are the three rates here, and you might even just make a separate column there. Then you can basically do this like we've been doing our AP questions. So you've got different concentrations of the I minus and the S2O8 2 minus, and you can see how those different concentrations are affecting the rate. Okay, so notice from experiment 1 to experiment 2. Well, it even tells you this. It says compare trials 1 and 2 to determine the order of the reaction with respect to iodide. How did the concentration change, and how did the rate change accordingly? What's the reaction order for iodide? Okay, I think you can figure that out. We've done enough of those by now that hopefully you can get that. Let's see here. Okay, so it's just asking about the iodide. And then which two trials should be compared to determine the order with respect to the persulfate, which is this one. So then they're asking you which two trials should you compare. Again, I think you can probably figure that out. You're looking for two trials where the I minus doesn't change, but the S2O8 2 minus does change, okay? And they're asking for the reaction order there. They're asking you to write the rate law for this version. So after you find the order with respect to I minus and S2O8 2 minus, they're asking you to write the rate law. Could the rate law have been predicted using the coefficients in the balanced chemical equation? Hopefully we know the answer to that question by now. This, to me, does not really look like an elementary step. Okay, so the stoichiometry is not going to tell us. And also, once you get the rate law, I think you're probably going to notice that it doesn't match the stoichiometry in the equation. So because this is most likely not an elementary step, or you could also say because the stoichiometry doesn't match the rate law, then no, we have to determine this experimentally. Okay. All right, number 2 here, an experiment is designed to study the rate of the reaction. So it's giving us some data here. And really not a lot of difference here between the first one and the second one, other than they've already given you the rate and molarity per second. And so you're just looking at this again, and this time they want you to actually find the value of K. Alright, so once again, we've done this a lot on our AP questions, but basically once you find the order with respect to the two reactants here, you're just going to do rate equals K times NO to the whatever power times O2 to the whatever power. And then plug in everything, like pick experiment 1, and we plug this in for the rate, and then plug in your two concentrations for NO and O2. Make sure to do whatever you need to with them based on the exponents and the rate law, and then you should be able to solve for K. And they want the It says the value for the specific rate constant. Make sure you put the units too. That's just good practice because they always ask that on the AP exam. All right, and then it gives us some data here. This is the one that you're not going to like on the pre-lab. Pre-lab is making you graph here, which you're also going to have to do for the post-lab. So it's good practice, but it's a little bit time-consuming. Basically, what you need to do here is graph this data. Okay, now make sure. Well, see, and they kind of guide you in that. You need to change your temperature into Kelvin here, which is what I forgot to do on the notes the other day. And then your rate constant gives you those values. And you need to find the natural log of the rate constant, okay? So once you find the temperature, then you take 1 over the temperature, and these two columns right here are the ones that you're going to be graphing, okay? Let's see here. Okay, once you find the slope is going to give you the negative EA over R. Okay, and remember R is 8.314. I believe it's joules per mole times Kelvin. I think that's right. Okay, so your activation energy is going to end up being in, should end up being in joules. So once you find the slope of your line, okay, whatever it happens to be, and I'm going to let you graph this and find it, then basically you need to find the, plug that in, so you've got slope equals negative EA over R, okay? So you got your R right here, you're going to know your slope, and then you just solve for the activation energy, okay? Resolve this. So there's your pre-lab. And already you can probably tell that this lab is just going to be crazy. There's a lot of work to it. Just missed one. Okay. Materials list and all that, we'll have that taken care of because you guys are doing this lab in class today. It tells the procedure. For part 1, again, you're finding the volume of 1 drop of a solution, so it tells you exactly how to do that. Part 2, we're determining the rate. The reaction rate and calculating the rate law, and you're going to use this table right here. And you need to try and get done with this today. That doesn't really matter because none of you are going to watch this video until after today, but we're going to try and get this part done at the very least today. And I think you can probably do that. You're just going to have to hustle a little bit on that part. So all of the experiments have the same total number of drops, okay? But we're varying the number of drops in each experiment. So if you notice here, experiment 1, we've got 2 drops of the Ki, 4 drops of distilled water, 2 drops of the HCl, 1 drop of the starch, 1 drop of the Na2S2O3. 2 drops of the KBrO3. Okay, so we're adding all these things together. Really, the things that we care about, the things that are in the net ionic equation, are the I minus, the H plus, and the BrO3 minus, I believe. So those are really the things that are the most important here. And when you add, I believe it's when it says when you add the KBrO3, that's when the reaction is actually going to start. Again, it's a little bit of a wasting my time, I think, to go over how the reaction or how the lab actually works, because we're going to be doing that in class today. But essentially, what we're doing is we're varying the concentration of the things that are in the net ionic equation, and then we're going to look back at those after we've measured the reaction rate, and then we're going to kind of decide what order these things are with respect to each of these reactants. Okay. So again, that's just telling you. Yeah, it says as the 2 drops of KBrO3 are added, you begin the timer. Okay. Just kind of slighted. So you're just going to do this several times. Make sure you collect good data. And then we're going to get to the activation energy part, okay? And again, this might have to happen tomorrow. Hopefully you can get done with the other part today. We'll see how far you get. So it tells you what temperatures you're going to want to use for this. We're going to measure the reaction rate at 3 different temperatures. Okay, and then it tells you basically how to do that. And then basically what we're going to do is like the pre-lab. Once we have the data for temperature and we can figure out our K for each of these, then we should be able to figure out our activation energy. Okay, and then determining or observing the effect of a catalyst on the rate. Again, we may or may not get to that part. Hopefully we will, but that's just going to show you what a catalyst does to the rate of the reaction. Okay, your data tables here. You've got a lot of data to collect, and make sure you collect it well. This is an important chart for the second part 2 here. You're recording the time in seconds, okay? And then, well, I'm sorry, actually, that is, yeah, determining the reaction rate and calculating the rate. That's right. So this first chart here is finding the volume of 1 drop of solution. The second chart here is determining the reaction rate and calculating the rate law. And so it's having you record the time in seconds, and the temperature in degrees Celsius. You need to know what your temperatures are there. Hopefully they stay pretty consistent. Then when we're doing the activation energy, we're doing it at 3 different temperatures. And you're calculating your K. Let's see here, and then there's the uncatalyzed versus catalyzed. Okay, and then this post-lab calculation stuff is going to walk you through exactly how to make these calculations. To calculate the volume of 1 drop of a solution, we're going to assume the density of water is 1 gram per milliliter. Okay, so the volume of 1 drop, what they're basically going to have you do is take the mass of 1 drop and divide that by the density, and then divide that by 1,000 to figure out how many liters there are in 1 drop. And so that, I think that's fairly self-explanatory. Let me go back up to the data table here. So having you find the mass of an empty beaker, then the mass of the beaker plus 5 drops of water, and then so then you'd find the mass of the first 5 drops of water, then the average mass. You're going to do it again. Just to be very sure on this, you're going to do 10 drops of water. You're going to take the mass of the second 5 drops, and then the average mass of 1 drop. And then you're going to put in 5 more, find the mass of those third 5 drops, and then take the average mass, okay? So you get the mass of 1 drop of water, okay? And then, like we just talked about, you're going to come down here and use that mass, divide it by the density, and divide it by 1,000, okay? Then to calculate the rate we're going to express, it's saying, as the change in the BrO3 minus with respect to time. And again, could have picked any of these things, but we're going to use that one. And let's see. In each reaction, there's 1 drop of the 0.0010 molar sodium thiosulfite. So we're going to have you calculate the moles, the S2032 minus ions. And it says the blue color begins to appear when all the thiosulfite ion is consumed. And the examination of these reactions allows us to calculate the moles of BrO3 minus, which react as all of the S2032 minus ion is used up. Okay, so then it's asking us for the moles of BrO3 minus reacted. So what we're going to have to do here on this part, to find the moles of the S2O3 2 minus, let's see, let me walk you through this a little bit just to make sure that we understand how to do this. We know the volume that we added, okay? So let's say that we end up just, your data is not going to be exactly like this, but let's say that we ended up calculating that we have 1.9 times 10 to the negative fifth liters of the thiosulfate. And the concentration here we know is 0.0010 moles per liter, okay? So we can actually use the concentration here. Sorry if that's hard to see. And then we're going to look at the stoichiometry in the equation, or the stoichiometry really in the formula, because that's the Na2S2O3. But really here, that's kind of an unnecessary step, because it's a one-to-one stoichiometry, okay? So for every 1 mole of sodium thiosulfate, we have 1 mole of the thiosulfate ion. So then that's going to give you the number of moles of the S2O32 minus, okay? So then, what we want to figure out here is the number of moles of BrO3 minus reacted. And what we're going to have to do is go back to, let's see which equation is it. I really want to turn all the way back there if I don't have to on the video. Let's see if I can find it here. Okay, you're gonna kind of have to do a two-step. Yeah, maybe I should go back to the equation just so I can really show this to you here. Once you find your moles of the S2O32 minus, then we can figure out how many moles of BrO3 minus reacted with that by coming back up here. And if you look at, really we got to look at this equation first, equation number 3 here, okay? Because the S2O32 minus here is related to the you can kind of do this one of two ways. I would relate it back to the I2, so we can figure out how much I2 we basically needed here. So if we figure out, the number of moles of this, then we can use the stoichiometry to figure out the moles of the iodine, or the I2. All right. So let's say again that we figured out, and again this is hypothetical. This isn't going to be your number. But let's say we figure out we have 1.9. Write this. Let's see. 1.9 times 10 to the negative 8th moles of the S2O3 2 minus. I'm sorry about how hard this is to read. Okay, so then what we're going to do here is using the stoichiometry in this equation, we're going to say, okay, for every 2 moles of S2O3 2 minus, I need 1 mole of I2, okay? And so that's going to tell me how many moles of I2 I needed in order to react with the S2O3 2 minus, okay? Because again, when the S2O3 2 minus completely reacts, that's when everything, that's when we see the blue color of the solution appear, okay? And so that's how much of the I2 we would need before the S2O32 minus is completely consumed. And that's going to be, using this example, that's going to be 1.9. I should be able to do this in my head. 1.9 divided by 2 is 0.95, right? So 9.5 times 10 to the negative 9th. Okay, so then you should get, I think it's 9.5. Let me double check on my calculator, actually. Mental math is horrible. 1.9 times 10 to the negative 8th divided by 2. Yeah, 9.5 times 10 to the negative 9th. That's how many moles of I2 that we ended up with here. I'm going to erase this now so I can show you the top equation here. Okay, so then we can say, all right, well, equation I'm really concerned about here, I want to know how much of the BrO3 minus needs to form before this reaction can take place. Okay, so now I can relate the I2 to the BrO3 minus, because this reaction kind of happens in two stages like this. But I need to know how much BrO3 minus do I need in order to produce the amount of I2 that would make this the color turn blue. Okay, and so I just said, I think 9.5 times 10 to the negative ninth moles of I2 is the amount of I2 that we need in order to get this reaction turning blue. Okay, and so I'm going to say, all right, I'm going to do my mole ratio of I2 to BrO3 minus, and for every 1 mole of BrO3 minus, I form 3 moles of I2. Okay, so then that tells me, once I divide that by 3, that I should need about 3.2 times 10 to the negative ninth moles of the BrO3 minus. Okay? And so basically I'm just taking it through that stoichiometry using those two equations, and that's going to give me the number of moles of BrO3 minus that need to react in order for this reaction to take place. Okay? Then, once we've got that, and whatever you calculate your concentration to be, because again, it's going to be different, then you're going to take that number. We'll figure out the concentration of it, and then we're going to figure out the rate. Okay, so now I would divide this by this number of moles. I'd divide it by the volume, the total volume. Okay, and the way I'd figure that out, each time we're using 12 drops in our experiment. So if you come down to the data table here. If you add up the drops, 2 plus 4, 6 plus 2 is 8, 9, 10, 12. Every experiment, if you add them up, you end up with 12 drops, okay? And again, let's say that we figured out that each drop is 1.9 times 10 to the negative fifth liters. And again, it's going to be different for you, okay? So 1.9 times 10 to the negative fifth liters times 12. That's going to give you your volume. Okay, so then you take that number of moles of the BrO3 minus that you found, and you divide it by the total volume of the solution, and that'll give you the concentration of the BrO3 minus. Okay, and then again, to find the rate of each of the reactions, now that we have the concentration of the BrO3 minus, which in our example, I think once you took the concentration we found at the BrO3 minus 3.0 or 3.2 times 10 to the negative ninth moles of BrO3 minus is what we found, and you divide that by the volume, which is 1.9 times 10 to the negative fifth liters times 12, because there's 12 drops there. That's going to give you your concentration, which would be 1.4 times 10 to the negative fifth. Okay, and then you just divide that by the time that it took to do the reaction in each experiment, and that's going to give you your reaction rate. So you divide this by, if your first reaction took 12 seconds, just divide it by 12 seconds, and that's going to give you a rate in molarity per second. Okay, so hopefully that makes sense and helps. I know that that's going to be probably your most complicated calculation right there. Okay, and this, I mean, it sort of walks you through it here. You find the moles of BrO3 minus reacted, and then it's going to tell you to find the concentration by taking the moles of BrO3 minus reacted divided by the volume of the 12 drops. And then it has you find the rate by taking the change in the concentration divided by time. Okay, and so then you're going to fill out this chart that has the different rates. Just a little recommendation for you on this. You don't have to do this, but it might be useful. Let's see here. later this charge setup. It might be useful for you to just copy the oh, okay, here we go. Yeah, never mind. As you calculate the initial concentration. So again, this lab is just, it's a monster. But you're going to calculate the initial concentration of each reactant for each experiment. Okay. Not be the same as the concentration in starting solution because they dilute. Once you add the 12 drops, they get diluted. Okay, so you're gonna have to do an M1V1 equals M2V2 here to figure out the concentration of each of these. And we're gonna substitute number of drops for volumes here, which is kind of nice. You don't have to worry about actually figuring out the actual volume. You can just use the number of drops. Okay. So it says find the initial concentration of each reactant and show the calculations. Okay. The way we're going to do that, an example of that would be like with the I minus. Okay. What we're going to do here is we're going to find the I minus concentration. That's supposed to be an equal sign. Let me fix that. You would say, okay, there are 2 drops of the iodine, right? So your initial concentration here for the I minus, you'd have to go up to your Ki, okay? And the initial concentration we use for the Ki, according to the lab, let me tell you what page you would find that on, just so you can see what I'm looking at here. Yeah, potassium iodide solution is 0.010 mole. That's on page 153 at the very beginning. Okay. And so then you would take that initial concentration, 0.010 molar, times your first volume, which is going to be 2 drops. And then we're going to set that equal to our M2 times 12 drops. And so then basically to solve for M2, we're just dividing by 12. Okay. That's going to give you your I minus concentration in experiment 1, okay? And so then what I would do here, this is just me, you're going to have to find the initial concentrations for 3 things, okay? We care about the I minus, the DRO3 minus, and the H plus, okay? Because those are the 3 things they're telling you are in the rate law. So what I would do is I would make a chart. And I'm just going to write over this thing and hopefully it's legible enough. I would make a chart that says, you got your I minus concentration, so you got your experiment number, 1, 2, 3, all the way down. You got your I minus concentration, you got your BrO3 minus concentration, and you've got your H plus concentration. I don't know why I put that so close here. Your H plus concentration. Okay, so those are your 3 concentrations here, and then what I would do is I would go ahead and put the rate right next to that, okay? So then you've got all these things, you've got your 3 concentrations and your rate, and then it becomes a chart just like the ones that we've got on the AP exam where you basically compare different things and you figure out what your rate is, okay? There's this huge, long thing that it tells you on here as far as how to calculate these things. I would not do it the way that they tell you to do it, okay? So this whole thing right here, where it says substitute the concentration values for experiments 1 and 2 into the equation, and then divide the first equation by the second, and all of this stuff, I wouldn't worry about all that, okay? What I would do is the way we've been doing it in class. I would just, so I'm not saying, well, actually, I guess I am saying don't even write this. Okay, don't even do this part. Just make your chart, okay? And then use your chart to figure out the rate, or the orders of the reactions with respect to each of the reactants. Just look at where it doubles and what happens to the rate when the concentration of I minus doubles, and then find where BrO3 minus doubles and everything else stays the same, just like we've been doing in class, okay? So then, the only part that you need to really worry about is write the number 4, where it says write the experimentally determined rate law. Right down here at the bottom, write the experimentally determined rate law. Okay, just do that the way that we normally do it. Okay. Then finding the rate constant from there should be fairly easy. It's just what we normally do. Just a little bit here. Okay, so then you've got experiment 1, and you're going to find your value of k for each experiment. So again, that's a little bit of a pain, and then you're going to find the average value of k. All right. So again, once you have your order with respect to each of your reactants, rate equals k times BR3 minus to whatever power times the H plus. I think I'm getting these in order. Times the concentration of the I minus. You'll have your whole reaction here, and the only thing you won't know is the K for each experiment. So you can solve for K for each experiment by plugging in your other data, and then find the average value of K. All right? Okay, almost done, sort of. So the activation energy part here, basically what we're going to do is we're going to use the data from part 3. We're going to calculate the values listed in the table below for each of the measured temperatures. Okay. So we're going to find our rate of reaction based on our different temperatures here. Okay. And once you find your rate of reaction and you know what your concentrations are, then you should be able to plug back into your rate law. Okay. Rate equals K times, and then all of your different concentrations here. Okay. So we know what our new rate is that we measured based on the new temperature, and we should be able to figure out what our rate constant K is going to be for each of these 3 different temperatures. Okay, the K should be different for each different temperature. When we change the temperature, we change the rate constant. Okay, so then you can find your measured temperature in Kelvin, find 1 over Kelvin, and then what you're going to end up doing here, just like in the pre-lab, is you're going to take the 1 over t, and you're going to graph that versus the natural log of k. Alright, and it even tells you ln of k goes on the vertical axis and 1 over t goes on the horizontal axis. Okay. Draw the straight line that's closest to the most points, the line of best fit, determine the slope of the line. Okay, and the slope again is negative EA over R, and it's giving you the value of R here, 8.314 joules per mole times Kelvin. And they want you to calculate the activation energy using that. Okay. So then, once you're finally done with all of that, and you have written down your data for the catalyst, we're not doing anything else with the catalyst other than just to see that, hey, it speeds up a chemical reaction. Then you've got some post-lab questions here. Okay, let's see if any of these are going to throw to you. Why does the reaction rate change? Does the concentration of the reactants change? So then you're going to be talking about collision theory on number 1 here. The more these things come into contact with one another, the faster the reaction occurs. Explain the general procedure used to find the rate law. Okay, you can explain what you did there. Why does the reaction rate change as temperature changes? Again, you can talk about the fact that it's all about collisions, right? So the faster these particles are moving, the more often they hit one another, and the more often the reaction occurs. Number 4, explain the general procedure used to determine. Okay, you can do that. 5, differentiate between reaction rate and specific rate constant. Okay, so reaction rate is the overall, that's measuring, change in concentration over time. Okay, the rate constant does not change unless you change the temperature. Okay, so you could maybe talk about there when reaction rate changes versus when the rate constant changes. Okay, so reaction rate, they're talking about this. Rate constant, they're talking about this. So you just need to talk about the difference between those two. Okay. Comment on the effect of the catalyst, and predict how the activation energy changes when a catalyst is added to a reaction. We know that. We've talked about that in class. A catalyst lowers the activation energy, which allows the reaction to happen faster. Make a general statement about the consistency of the data with calculated orders close to integers. Okay, this is where you get to talk about how close were your results to what might be expected for this reaction. Um, Number 8, write out the 2-point form of the Arrhenius equation which relates rate constants temperature. That's kind of a weird thing to do, but I guess, I mean, all the rest you need to do there is just write an equation, so that won't take you very long. And then number 9, how could you improve the data? So now you're thinking about, you know, how could we actually make this better? So, anyway, that is the kinetics lab, and that's going to give you a fun 4-day weekend. I apologize for that, but actually there's probably not a better time to put it because it's going to take you a long time. So good luck with that. Hopefully you really understand kinetics after you're done with this. All right, see you in class.